Good afternoon, everyone. Today I will be presenting my study on machining response in lathe operations as part of my experiential learning topic in robust design. My name is Girish S. and this study was conducted under the guidance of Dr. Bartish A. The aim of this study is to analyze how machining parameters, spindle speed, feed rate, and depth of cut affect the chip formation in the lathe machining. And coming to the introduction part, a lathe is a machine is one of the oldest and mostly widely used tool in the manufacturing. It rotates workpiece against stationary cutting tool, remove the materials, and it is used in various industries like automotive, aerospace, and industrial manufacturing to produce high precision and cylindrical components. And in this study, we are investigating how different cutting conditions affect chip characteristics like chip thickness and which are crucial for optimizing machining efficiency. This is the introduction part, and coming to the objectives and study. The primary objective of this study is to develop the regression model that predict the chip thickness and based on the key machining parameters such as feed rate and depth of cut and spindle speed. And also we will use also the ANOVA analysis to check the significance of these parameters and their interactions. And the main objective is why is this study is important. It helps in optimizing machining efficiency, and it reduces the experimental effort by using statistical modeling, and also it improves the tool life and lower the manufacturing cost. And we can relate these objectives in the real world, and by this understanding these responses can help industries optimizing machining process, reduces cost and enhance productivity. And coming to the procedure part, and we will first we set up the workpiece operations, and the workpiece is secured and lathe check and ensuring the tool properly aligned, and setting the parameters such as spindle speed, feed rate, and depth of cut are adjusted based on the experimental plan, and performing the machining operations. In the lathe operated, each set of parameters and the chip are collected after machining, and make sure measuring the chip thickness by using and recording the analysis and data. The chip characteristics are recorded and analyzed for the trends. And coming to the experimental setup and design of experiments, here we used operators such as lathe and workpiece as a aluminum, and material we used HSS or carbon steel. The factors we are considering such as feed rate, depth of cut, and spindle speed. Here we have 18 experiments we have to conduct it. We selected the different levels for each factors such as feed rate for 3 levels and depth of cut for 3 levels, and spindle speed we can take it as a 2 levels, and feed rate we can take it 0.1, 0.2, and 0.3 mm per revolution, and depth of cut is 0.5, 1.5 mm per mm, and spindle speed is 500 to 1000 rpm. The total experiment by using full factorial design we conducted 18 experiment. 3 into 3 into 2 is equal to 9, and these levels are representing common industrial cutting conditions for optimizing machining responses. And coming to the tabular column, here this table presenting the collected data for all 18 experiments including spindle speed, feed rate, and depth of cut, and each corresponding chip thickness. And by analyzing these values we can identify the trends in machining responses. Here we identify that here the chip thickness is increases with the feed rate, and also depth of cut affects material removal but has minimal impact on the chip thickness. And coming to the analysis procedure, here we develop the analysis procedure by using minitab software. Here these are all the steps I will explain by using analysis, by using these procedures, by using minitab software I will explain.
at dy factorial, create factorial design. Here there are different types of designs are there. I am going to take full factorial designs, and I have 3 factorials in my experiments and make it as a 3, and general factor full factorial design and make it as a 3, and display available designs, and name the 3 factors we have. Speed, the speed is in rpm, and b feed rate per revolution, and the third factor is depth of cut in depth of cut in and number of levels, of speed in 2 levels, and feed rate in 3 levels, and depth of cut in 3 levels, and put the number of replicants same as it is 1, and click ok, and go to factors, and here we seen that all factors are already created by the mini tab. Here we observe everything is correct, 3 levels everything is correct. Click ok, and coming to results, summary table, ok, and click ok. Here we observe the design summary. We already upload 3 factors based on 18, number of experiments is 18, and number of levels is 2 3 3. Here we see the tabular column. We observe 18 experiments it already created, and here we observe that but it created randomly, but same not it is not same as our values. We have to replace these values by using by experimental values, and by copying it from the excel and paste it here, and chip thickness, and this is the response we are going to add now. My response is chip thickness in mm, and now we are going to add the chip thickness response, and we are in the excel sheet we have the chip thickness values. We have to copy it and paste it here we already paste, and then now this is the chip thickness. We have going to add this chip thickness into the design. DOE factorial analyze factorial design, chip thickness select, and this is a response. But these are go to terms all, add ABC, these are all the selected terms, and click ok. No change in covariance, no change in options, and stepwise ok. Graphs, we want 4 in 1 graphs: histograph, normal plot, pressure plots. These are all the graphs we want in only one plot. That's why I'm clicking 4 in 1, and 4 in 1, and residual, and click on the residual versus versus available, and storage, and we want fits and residual stresses. Okay, clear, click ok. Here we observe that residual versus fits residual graph, and also minitab is created the fits and residual false values, and also it created the analysis of variance. These are all the factors informations, and speed rate in 2 levels, speed rate in 3 levels, and depth of cut in 3 levels, and also where we see in the analysis of variance. These are all the f values and p values. 0 to 0.9 are the p values, and also model summary 99.25%, and where we observe the coefficients of values of p and values of t values, and this is a regression equation, and these are all the Pareto charts and standard effect created by the Minitab. By giving the response of the chip thickness, here we get the fits and residual stresses different types of crops, and these are all the residual plots for chip thickness, and these are all the all four graphs are obtained in one graph, and these are all the interactions part. We want interaction part, that's why we are going to do a factorial define and factorial plots, and click on the factorial plots, and speed, feed, and depth of cut we observed here. These are all the factors we observed. You just change the display terms into all terms and click options. Okay, there is no change in options. Click on graphs, and these are all the main effect plots and interaction plans we want right now. That's why click OK, close, and OK, close. These are all the, here we observe that main effect plot from the chip thickness, and also interaction plot for chip thickness. Here we observe that speed, feed, depth of cut, and the by considering the all the factors 500 for speed, and feed rate for 0.1, 0.2, and 0.0, and depth of cut is 0.1. Thank you.
And coming to the results and graphical analysis, here we see that the results from the Minitab confirms that all three machining parameters significantly influencing chip formation. And here we observe that higher feed rate, increase in chip thickness and chip length, and depth of cut affect the chip formation but has minor impact on the chip thickness, and higher spindle speed improves the surface finish but many increases tool wear. The the graphical representation, here we see the graphical representation. Here we confirm that factors information, here we these are all the factors: speed, feed, and depth of cut. These observations are observed from the Minitab softwares. And levels, here we can observe we are selecting 2 levels for speed, and feed rate 3 levels, and depth of cut 3 levels, each factors containing the each values. And the analysis of the variance, here we also observe these are all the factor information, and this is the analysis of variance. This is a model summary for all factors, it's showing model summaries. And here we observe the results of by giving charts. The different charts were developed from different levels. At by observing Pareto chart, it shows which factors have most impact. And also here we see in the main effect plot, shows that each factors individually affect chip thickness. And also interactions plots, these are all the main effect plots. And interactions plots explain how factors influencing the each other. And these are all the graphs we obtained from the Minitab software. After, and coming to the conclusion part, and this study confirms that feed rate has the most significant impact on the chip thickness and chip length, and depth of cut plays a role in a material removal but has a lesser impact on the chip thickness, and high spindle speed improves the surface finish but could increase the tool wear. And this is research helps in selecting the optimal machining parameters for improved tool life, lower cost and better productivity. The future studies focus on other materials, tool coating and other optimization method. Thank you.